Hi, what this video is going to have a look at is the vector solution to the following problem. We want to show that the midpoints of the sides of a quadrilateral join to form a parallelogram. So we're going to have a look at these diagrams down below. So we're starting with ABCD, which is a parallelogram. So A, B, C, D. And we've got the midpoints, and they're F, G, E, and H, or E, F, G, and H. So we know a bit of information already. We know that that is a quadrilateral, so a four-sided shape. Okay, we don't know that that's a parallelogram. We don't have that information, but the midpoints of the sides of that quadrilateral, we want to show they join to form a parallelogram. So we want to show that E, F, G, H is a parallelogram. Now we know information along the lines of that E is halfway across AD, so we know that AE would be half of AD, and we can do that for each of the sides. So we're going to come up with a fairly long-winded proof of this, but it's fairly basic once you get onto a roll of what's happening. So we're going to be working in small triangles, and like the proof that I did above, if you've seen it, then move into bigger triangles and try and get a relationship from our four-sided quadrilateral that moves into, it moves into the small shape inside with the midpoints on the edges. So let's first of all write down what we know. So if you like to mark your shapes, you could mark it such that we know those are the same distance, those two are the same distance, those are the same distance. Oh, it's a lot of dots and dashes, and those are the same distance. And noting this needs to be a vector proof. Okay, not just a plain old geometry, non-vector proof. Okay, let's see what we can do. Okay, so I'm going to work in this section of the triangle first. You could work in any of the four corners, but that one's probably the easiest to see. So what do we know about that? Now we know that FG, so I'm going to put that direct vector in that direction. So that vector FG is equal to, using our triangular addition, that would be equal to FB plus BG. So I'm going to pop the vectors in that direction. Vector FB plus vector BG. If yours are going in another direction, that's okay, as long as you keep them in that direction all the way around. Okay, oops. Now what do we know? We know that vector FG, although it is equal to FB plus BG, we know that FB, this small vector in here, is half of the vector AB, because we were told that F is the midpoint. So we know that this section and this section are equal. So I'm going to replace vector FB with half of vector AB. And I'm going to do the same for vector BG. So vector BG is a half of vector BC, because G we know is the midpoint of that side, so each part, either side of G is equal. So half of vector BC. I'm just going to pull that half out the front. So we've got half, and we've got AB plus BC. Okay, now what we can do, remembering this is vector FG, that's going to be equal to a half of, if we go back to our triangles up there, AB plus BC. Well, where's AB? There's AB. There's BC. I could draw another dotted line here. I'm going to use this one. Could be bold. I'll just do it dotted because we've added it in. Okay, so triangular addition. Okay, AB plus BC. AB plus BC is going to be equal to AC. Okay, so FG is a half of AC. If you're working with me in the classroom, that would have seemed very familiar to the proof that you would have done up above, which was this one. Okay, so we first of all had a look at a triangle like here, and we had to show that the line joining the midpoints of the two sides, they're parallel, but it's also half the length. And that's what we've basically just proved here. We've done that again, and we've done that in working in this triangle in here, and we're saying that FG here is going to be half of that vector AC. Now what we are going to do is work in that quadrilateral, but I'm going to move down to this bottom section down here. Okay, and I'm going to work in this small triangle here, doing exactly what we did up above. Okay, and I'm going to show you that EH, that vector there, is equal to ED, okay, that direction there, plus DH. So we know that by the laws of vector addition, so we'll just pop that one in. EH is ED, oops, you can see there, plus DH. Okay, so what we're going to do is do the same as we did before, and we know that ED is a half of the side AD. And we know that DH is going to be a half of the side DC. So if I again factorize out that half, remembering this is what EH is equal to, what I'm going to end up with is that EH, or vector EH, is going to be equal to 1/2 of, well, what's AD? Move back over to that diagram, plus DC. AD plus DC is going to be AC. Okay, so what we've now gotten is two equations, our original one that we found and our new one, which is a little bit smaller there. And what we'll find is in both of those equations, we've got a half AC and a half AC. So they're equal. Okay, so what we can say is, if we sub 1 in 2, vector FG is equal to vector EH. So what have we got? The vector FG, this one here, is an equal length to EH. We're on the roll there, and it's sort of at the point where we're looking at it being a parallelogram, possibly. Since we know that FG is equal to EH, and we're talking in vectors, because they're vectors, vectors that are equal are in the same direction. So not only are they equal, we can say that vector FG is parallel to vector EH because of the rules of how vectors work. Now, I'm not going to do the other two sides. I'm just going to write similarly in this case. But similarly, I can do the same two proofs there for the other two corners. And what I will end up with, I just might write similarly here. Similarly, I'm going to get that vector EF is a half of vector DB. And I would also get that HG is a half of vector DB. So I'm going to leave that to you to have a go at yourself following the same rules. And so like I've gotten over there, okay, we can call that 3 and 4. If we pop those together, what we end up with is that vector EF is equal to vector HG. So we've got them equal in size, and we've got them equal in being parallel because vectors that are equal are going in the same direction. So we can say that. Okay, so therefore we can sum it up. Since the opposite sides are equal and parallel, what have we got? We have a parallelogram. And then we can say EFGH is a parallelogram. So it's a fairly easy proof. It's just a little bit long. Okay, I don't think you'd get one like that in your HSC. It's a little bit too long. But I want you to go, if you're in my class, go home, and I want you to practice seeing if you can get this proof out without me being there to assist you.